let's have a look at the laws of exponents. The laws of exponents are all just facts about how exponents work. They aren't really, they aren't arbitrary rules that we've made up. They're actually patterns that follow from just the definition of what powers mean. So let's just have a look at how these laws of exponents work out. So one of them is if you have a product and both pieces of the product have the same base for your exponent, then it turns out that you can just add the exponents like this. Okay. The reason for this is, just as an example, if you have, say, a squared times a cubed, well, the a squared is a times a, right? There's 2 copies of a there. And then the a cubed is a times a times a. There's 3 copies of the a's there. And so there's 5 total. So this is a to the 5th. So, you can see that this proves this fact of exponents for integers, for positive integer powers. But then we define fractional powers and negative powers specifically so that this pattern will still be true. So, all right, so when you have a product with the same base, you can just add the exponents. All right, what if you have a quotient with the same base? Well, then you can just subtract the exponents. There are a couple ways to see this. One nice way is, we can write this as a to the n times a to the m times 1 over a to the n. But 1 over a to the n, by definition, that's a to the n minus, a to the minus n. But then we can use the product to addition formula that we just talked about to add these. So we get m plus negative n, which is m minus n. Okay. Another way to look at this is really just a fancy way of canceling common factors. So, if you had a fraction like this with positive powers of a, the numerator is a times a over a times a, but then, right, an a cancels, right? When you simplify this fraction, you just get a to the first, and, right, 1 is 3 minus 2. But again, we define negative exponents and fractional exponents so that this pattern still holds even when m and n aren't positive integers. All right, next up is what if you have a product to a power. So it turns out that the power kind of jumps onto each part of the product like this. Again, for positive integers, this is pretty straightforward to see. For example, if it's cubed, well, a times b cubed, that's ab times ab times ab. And then we can rearrange this, so it's a times a times a times b times b times b, but that's a cubed times b cubed. So you can see this kind of argument works whenever n is an integer, but again, we extend the definition of exponents to fractional exponents and negative exponents in a way that makes this pattern still hold. All right, final law about exponents is what about a power to another power, like this, so a to the m, and then after that to the n. So this is a to the m times n. And, once again, if we just do an example with integers, you'll see that it's true for integers. But again, we define fractional powers and negative exponents specifically so that this pattern will still hold. For an integer example, right, a squared cubed, that's a squared times a squared times a squared, right? But now there are 3 copies of that too, and so when you add them all together using the sum property, which is way up there, you get a to the 2 plus 2 plus 2, but that's a to the 3 times 2, right? Because there are 3 copies of 2 here, so it's 3 times 2. All right. Now I keep saying that we define negative exponents and fractional exponents to extend these patterns, but what are those definitions? Just remember that a negative exponent is 1 over that power, and in fact this is even true if n itself is negative, right? So if you have, say, a negative here, this is on the one hand a to the negative 2, that's a squared, but on the other hand it's 1 over a to the negative 2, but that's 1 over a squared, but that's a squared, right? So all A fractional exponent, so a to the 1 over n, that's the nth root of a. All right? That's just by definition, but again, the reason that we choose this definition is because it makes all these patterns, all these laws of exponents work, even when the exponents are fractions. Notice that this definition only defines a fractional exponent that is the reciprocal of an integer, at least at first. But in general, if you have any rational exponent like this, you can write this as a to the 1 over n to the m. So this is the nth root of a to the mth power. Or if you like, you can actually do the root on the outside. Oops. The root on the outside and the power, the integer power on the inside. All right. Last example, what is a plus b to the n? So what's the rule of exponents for this situation? Well, there isn't one. So it's a popular algebra mistake to think that this is a to the n plus b to the n, but that's just not true. Okay? There might be very special cases when this is true, but in general, this is not true. Just as an example, try 1 plus 1 squared. Right? Now 1 plus 1 is 2, and 2 squared is 4. So what this actually is equal to is 4. But what about 1 squared plus 1 squared, right? If we thought that these things were equal, we would think these two things were equal. But is 1 squared plus 1 squared equal to 4? No, it's equal to 2. So you can see these two things aren't equal in general. Probably the most common situation where I see people make this mistake is this situation. If you have, say, x squared plus 9, or the square root of x squared plus 9. Now, a square root is really a fractional exponent, right? And we just said that you cannot put this exponent on each piece, right? So the common mistake is people see these perfect squares inside, they see the square root, and they think, oh, I can just take the square root of each piece separately. So this should be x plus 3. But that's not true. Okay, if you graph these, you'll see they don't make the same graph. Also, if you just pick a number and plug it in to both sides, you'll see that it's just not true. For example, if we pick x equal to 4, that is an example that sort of makes some nice integers. So if x is 4, on the left-hand side, 4 squared is 16. So square root of 16 plus 9, that's 25. So we get 5. On the right-hand side, if we plug in 4, 4 plus 3 is 7. And 5 is not equal to 7. So this is probably one of the most common mistakes that I see in algebra, so don't make this mistake, right? If you have a sum inside of an exponent, in general, there's no simplifying you can do, at least not immediately. There might be some fancy tricks in special situations, but in general, there's no sum rule for exponents. All right. Let's look at a few examples of using these exponents to simplify expressions. So these are the sorts of expressions that only ever show up in algebra books, but let's simplify them anyway. So we could either start at the outside and sort of deal with the exponent that's way out here first, or we could start with the inside. I kind of like to start with the inside, so let's leave this minus 3 alone. So notice that we have some factors of a. So there's no factor of 2 in the denominator, so that's just 2 to the first. For a's, we have a to the minus first divided by a squared, and so we can do minus 1 minus 2. Right? Any exponent in the denominator sort of turns out negative when you combine them like this. For our b's, we have b in the numerator, it's just b. In other words, b to the first. And then the other factor of b is in the denominator, so this is minus negative 3. Okay. So this is 2 times a to the minus third times b to the minus second. Okay, and this whole thing is to the minus third. Now remember, we have a product here, right? These things are built out of products, so this exponent distributes onto the product, across the product. Okay, so this is 2 to the minus third times a to the minus third to the minus third times b to the minus second to the minus third. So 2 to the minus third, that's 1 over 8. Right, it's 1 over 2 cubed. 2 cubed is 8. And then a to the minus third to the minus third, that's a to the minus 3 times minus 3. That's positive 9. And then b to the minus second to the minus third, that's b times, or b to the negative 2 times negative 3. That's positive 6. All right. So 1/8 times a to the 9th times b to the 6th. If you wanted to, you could move the a's and the b's into the numerator of this fraction like this. This isn't really necessary, but if you wanted to, you could do that. All right. Second example, let's simplify this. So here is where this common algebra mistake shows up. So it's a very common mistake to say, well, this is the square root of 81x to the 4th plus square root of 27x squared. And then, then there's further simplifying. You can do square root of 81 is 9, square root of x squared, x to the 4th is x squared, plus square root of 27 is 3 root 3, I think. And then square root of x is absolute value of x. Or sorry, square root of x squared is absolute value of x. But again, this is false. This isn't right. Okay, so if this simplifies at all, we're going to have to find some other way to simplify it. We can't pretend that we can break up square roots across a sum like this. We could if it were a product, but not a sum. Square roots don't break up across sums. Well, for this particular example, I see that these two pieces of this sum actually have a lot in common. So inside of this square root, let's see, they have a 27 in common, a factor of 27, and they have a factor of x squared in common, like this. And then the stuff that's left over is, I guess, 3x squared plus 1. Okay. Well, now we have this written as a product, right? There's a product here and here, so we can use the, right, the square root is really an exponent of 1/2, so since exponents distribute across products, so do square roots. So we can break up this square root across these products. So it's the square root of 27 times the square root of x squared times the square root of 3x squared plus 1. Okay, now the square root of 27, that's 3 root 3. Square root of x squared is the absolute value of x. And the square root of 3x squared plus 1, right, this is the square root of a sum. Unless we have some other algebra tricks up our sleeves, we can't simplify this anymore. So this is just square root of 3x squared plus 1. And this stuff inside this square root is simple enough that there aren't any other tricks. So we're going to have to leave this square root the way it is. If we wanted to, we could put these two square roots back together. This isn't really necessary, but if you wanted to, you could write 3 times absolute value of x times 3 times 3x squared plus 1. Okay, so one of these two, I would say, is done simplifying. Okay, last example, this mess. I realized I left off a law of exponents, which is if you have a quotient to a power, that power hits both pieces of the quotient like this. That actually follows from all the other laws of exponents, so maybe it wasn't totally necessary to list it, but it's a fact. So in this first piece, we can actually take this fourth power and stick it onto both of these pieces. The second set of parentheses let's leave alone for now, so x to the minus second over y cubed. But in this first set of parentheses, it's x to the 1/2 to the 4th, so that's x to the 4/2, that's x squared. And then in the denominator, it's y to the minus 1/2 to the 4th, that's y to the minus 4/2, that's y to the minus 2. All right. Before we go any further, maybe we should deal with these. Well, actually, no. Let's do it this way. There are so many laws of exponents. There are a lot of options for how we could handle this. The way that I'll handle it, I guess, is actually multiplying these fractions. So x squared times x to the minus second over y to the minus second y cubed. Now we can combine our, right now we have products with the same bases, so we can combine the powers. So in the numerator we get x to the 0, and in the denominator we get y to the 1st. And x to the 0, that's 1. All right, so we're done.